Comparison test, video 2. In video 1, we introduced the comparison test. Here in video 2, let's do some examples. The comparison test may be used to determine whether a series converges or whether a series diverges. Here in this example, we're going to end up showing that the series diverges. That's a statement on the series given by the BNs. The comparison test requires that the sequence of BNs needs to be, term by term, after some index, bigger than a series given by ANs, where that series in ANs we can determine diverges. That will force the series given by the BNs to diverge. So the first example. Looking at the series, its given associated sequence looks basically like the harmonic if you ignore the -1 and you ignore the coefficient 2. All right. Let's see. Does that -1 work to our favor? Set it up. 2n minus 1 is less than 2n. Thus, their reciprocals will have a relationship with the inequality in the other direction. This is the sequence of the series given to us. Here is a sequence for which we have information. In other words, this is 1/2 1 over n, and that is 1/2 of the harmonic series, and the harmonic diverges. Thus, this AN determines a divergent series. With our BNs bigger than these ANs, and the AN giving something which diverges, we conclude that our series diverges by the comparison test. Nice. Let's look at the next one. Here we're going to conclude that the series converges. If we want to conclude that the series converges, we need to be able to compare it with terms that are larger, yet we know define a convergent series. We want to conclude convergent. So these terms here are the ANs. Let's investigate what they look like. With that factorial, try and find cancellations. In the denominator, you have n plus 2 quantity factorial. That can be written out as n plus 2 times n plus 1 times n factorial. With the cancellation, we see that in the denominator, there are 2 copies of n. That's essentially a p-series with p equaling 2, i.e., yeah, this is probably going to converge. We want to use the test CT to show that. We need to find a sequence that is larger term by term. All right, so set this up. If we have n plus 2 times n plus 1, that's going to be bigger than n plus 0 times n plus 0. But n plus 0 times n plus 0 is n squared. Taking the reciprocal of both sides leads to the good inequality. With the good inequality, the series determined by these ANs are smaller than the sequence given by the BNs, and we know that the BN determines a p-series which converges. So we have the bn's being large, check. And then we also have that the bn's converge, check. So that's 1 and 2 satisfied, 1 and 2 satisfied. We get to make our conclusion. The given series converges by CT. Nice. Let's look at the next one. Now here we need to pay a little bit attention to this numerator. So in the numerator was sine of 1 over n. The behavior of 1 over n is going to 0 if the n in the bottom gets big, and sine at 0 is 0. Something that we'll make use of is the fact that sine in magnitude and its size is less than its input. And dividing both sides by absolute of x leaves us with the ratio of sine of x over x is less than or equal to 1. Good. Here's our an, sine of 1 over n over n. Let's multiply by 1 in the form of n over n. We can keep the n in the bottom with the n in the bottom, get n squared. The top multiplied by n is the same thing as the top divided by the reciprocal of n. And the fact that we just made note of, sine of 1 over n over 1 over n is less than 1. Hence, we have our an term being less than or equal to bn's, where the bn's we know is defining a p-series which converges. Go through our checklist. We have condition 1, the good inequality. Condition 2, the bn's converge. Therefore, we get that our smaller guy also defines a convergent series. What are we using? The comparison test. Very nice. One more. So here we're again going to get convergence. If we look at our associated sequence, we can ignore lower order terms. Completely ignoring those guys, we can then consider 1.2 taken away from 2.3 leaves you with a value which is strictly larger than 1. So we can compare with a p-series. Okay, let's set that up. Start with the denominator. Something plus 1 is going to be greater than that something. Produces the reciprocal relation. Then these quantities, if we multiply by n minus 1, n to the 1.2 minus 1 on both sides, but then we can get even larger if we throw away the minus 1, and then n to the 1.2 over n to the 2.3 will simplify to this. And negative 1 over n to the 2.3 is itself. And these are each convergent. Therefore, the bn determined by their difference is convergent. So we can state that here, that on one hand, p equaling 1.1 defines a convergent series, p equaling 2.3 defines a convergent series. Nice. So we have the good inequality, and we have that the BNs determine a convergent series. Therefore, the given series converges by CT. Excellent.